look at a large library shelf and see a single gap between the books, your first instinct might be to slide the volumes together to make it look neat. But in data science, that absence is actually a piece of evidence. The gap itself is telling you a story that requires investigation. Let's apply this to a real-world dataset. We have a table containing the dimensions and prices of 10,000 individual diamonds. But as we scan through the records, we spot a specific gap. 500 of these diamonds are missing their width measurements. Looking at this data frame, we can programmatically locate and tally these empty spaces. By running df.isnull.sum, we scan every column and count the exact number of blank cells, quickly diagnosing the scale of our missing data. We have to address these 500 gaps before we go any further. Machine learning models cannot perform math on empty space. If we try to feed this raw table into a predictive algorithm right now, the model will simply fail to train. This animated diagram shows the most common beginner instinct, deleting the problem. If we use df.dropna, we delete any row with a missing value. The table shrinks, giving us a complete dataset. But watch the demographic chart next to it. By deleting those rows, an entire category of premium cut diamonds vanishes from our analysis. Deleting rows is only mathematically safe under one strict condition. The data must be missing completely at random, or MCAR. That means the blank cells have no underlying pattern and aren't related to the other variables in your table. If the data isn't missing at random, say the premium cuts were skipped during data entry because they require a different measuring tool, our deletion introduces severe selection bias. We have just slashed a specific subgroup out of existence, completely warping the reality of the remaining data. Let's try the second beginner instinct. Instead of dropping rows, we use df.fillinZero to keep our row count intact by replacing every blank space with a 0. This scatter plot maps diamond width against price. By injecting zeros, 500 expensive diamonds are suddenly slamming into the y-axis. A diamond with a width of 0 millimeters is physically impossible. By filling the gaps with zeros, we preserved our row count, but we broke the mathematical reality of the dataset. We have to find a smarter way to bridge this gap. This histogram displays the natural bell-shaped distribution of our diamond widths before we alter anything. The standard industry solution here is mean imputation. We use SimpleImputer to calculate the mathematical average of all the non-missing widths, and we inject that exact average into all 500 gaps. Take a moment and think about the geometry here. If we take 500 identical averages and drop them straight into the middle of this dataset, what is going to happen to the shape of our data? We get a massive spike directly in the center. The row count is fixed, but the natural variance of our dataset is artificially compressed. We have created a false sense of certainty, grouping hundreds of diamonds into the exact same profile. To fix this, we use an advanced technique. Before we impute, we create a new Boolean column. We write df.width was missing equals df.width.isNull. This explicit flag tracks exactly which rows are authentic and which rows contain our injected averages, marking the artificial ones with true. By flagging the imputation, we feed the model the full story. We tell the predictive algorithm, here is a reasonable guess for the width, but treat it as a guess. We've taken a missing data problem and turned the fact that it was missing into a highly predictive feature. On this split screen, we can compare the actual predictive accuracy of our choices. Model A dropped the rows entirely. Model B used mean imputation but hid the tracks. Model C used mean imputation paired with our Boolean missingness flag. Because Model C had the context to separate reality from our averages, it clearly outperforms the other two. Here is your consolidated workflow for missing data. Step 1, identify the gaps using isNull. Step 2, assess for MCAR. Determine if the data is missing completely at random. Step 3, act. If the missing data is random and small, you can drop it. If it's large or systematic, use SimpleImputer and track your tracks. The choices you make about what you cannot see dictate the accuracy of everything you can. Data science is about preserving the context of your evidence, even when it's empty space. But what happens when a data point isn't missing, but its recorded value is completely impossible? What if our table says a standard diamond is 59 millimeters wide, making it over 2 inches long? In the next lesson, we will tackle the exact opposite of a gap, the anomaly.